We're going to start by thinking a little bit about loops of current. Now, loops of current were one of the shapes that we used integration and Biot-Savart to actually calculate. However, when we did that calculation, it was only for on-axis, meaning this line through the center. And so we can use that equation if we want to get the magnetic field strength, and then we can use the right-hand rule to get the direction. However, we can start to understand a little bit more about the shape of this using symmetry. This object, this current loop, has rotational symmetry. Now, one thing to notice in this picture is that you can clearly see that the object is three-dimensional, but here we're only looking at iron filings on a plane. So we see just a two-dimensional picture which shows one cross-section through what's happening in our ring. One of the reasons I like this picture is because you can clearly see that this represents what you're frequently going to see in the book, where one side you have a circle, the other side you have a circle. Now, we don't have enough information in this picture to see for sure, but we could say that at the top it's coming out of the page, the dot's in the center, and on the bottom it's going into the page, so there's an X. We don't quite worry about the details here, but then you see these kind of distorted circles. And what's helpful to think through here is that you know when you have a line of current, the magnetic field goes in circles around that line. Now we've taken that line and kind of bent it end to end to get a circle. So you can see that there's kind of a circle here, and there's a circle here, and there's going to be some sort of circle out here. So we do still have circles, but now they are a little distorted, so they're not exact circles. And you can see that that also means that at the very center, because of this distortion, you actually start getting a field that's kind of a little bit straighter, right? So that's what it starts to look like. So we can use symmetry arguments to think through what this must look like, but obviously it's going to be helpful if we try to do some accurate pictures of this using field vectors and field lines rather than just using iron filings. We now have two pictures showing our ring, and again note that we have the circle at the top, meaning current's coming out of the page there, and X at the bottom means that current is going into the page there. And again, you see these circles that do get a little more distorted as you go out, and they're not exactly centered on the wire, but they're close. So again, keep in mind that the field vectors are tangent to the field lines, and that the larger field vectors mean that your magnetic field strength is bigger. So we see that we have reasonably strong field strength in this region. So one of the things here is that, again, it's still a two-dimensional picture. This magnetic field is too complicated to really try to show it in a 3D view. It's just not that easy to do. So instead, what's helpful is to actually just show two different views. This is our side view, and then this is a face-on view. Notice that here it says seen from the right. Why does that matter? Well, you kind of get the opposite field whether you're looking from the right or from the left. So again, the way physicists sometimes show this is they actually draw your eyeball to show how you're actually looking. So we are looking from the right, and notice that these field lines are coming at the eyeball. And so what we see here is that these field lines in the center are coming out at us. But notice that then, out here, we would have the field going away from the eyeball, right? Because your circle's going that way, so your field is actually going away on the outside, and we see it's going away on the outside. So neither of these captures the entire details of what's happening here, but the two of them together give you a fairly good picture of what's happening. So effectively, this picture is only giving you a cross-section through this very center, but then this picture is giving you a cross-section through here. So each of these really shows you a plane, but together you're able to see what's happening. One of the things that you need to be able to do for either of these representations is actually use the right-hand rule to get the direction. You can see that the field is entering the left and exiting the right. If we reverse the current, it would go the other way. But we also have this view up here. So there's some right-hand rule stuff we can do here. One is to curl your fingers in the direction of the current. So that's useful if we first start thinking about the picture on the right. So if I try to make my fingers curl in the counterclockwise direction, I see that my thumb points out of the page. In that case, the thumb is telling you about what's going on in the inside. You can use the same right-hand rule for the left picture, where again I need to curl my fingers in a way where they come out at me at the top and go into the page at the bottom. Then again your thumb points to the right. So when you use that style of right-hand rule, the thumb is telling you what's happening on the inside. So there's two ways that the book presents it, and the one I just described is actually number 2 here, that you're curling the fingers of your right hand. Again, remembering this is the right-hand rule because you must use your right hand. Put down your pencil if you're right-handed. So if you curl your fingers in the direction of the current, your thumb points and be on the inside. On the other hand, you could actually point your right thumb in the direction of the current, and the way that your fingers curl around at that point actually tells you the way that the magnetic field is going. So let's go back and look at that. So let's look at this point at the bottom. That X means the current's going in. So if I point my thumb into the page, my fingers curl this way, and that tells you that your magnetic field is making circles in the clockwise direction there. So that's kind of the way to use these two right-hand rules, is you can either think about the magnetic field just overall on the inside and fingers as current, or thumb as current and fingers then tell you the magnetic field.